Okay, so in the universal law of gravitation, with this formula, you have dealt with the interaction between mass 1 and mass 2, separated by some distance r. Keep in mind that the r is actually a distance, the distance from core to core, from center of gravity to center of gravity, okay, not just from the edge. So that's always the how the r is measured. So that's pretty easy what we've done before. But what happens when you have more than two masses that are present? And in most cases in reality, there's more than two masses always, right? I mean, look at us here. We got all these people sitting. I'm mass 1, mass 2, and so on, right? You got mass 2, mass 3. We have a lot of masses. And guess what? Each mass is pulling on the other masses. So I'm going to look at Carl, UJ, and Mary Beth, for example. There are three of them, right? UJ is sitting right in the middle. What can you say, where would UJ be attracted to in terms of gravitational force? You've got Carl, let's call him mass 1, UJ is mass 2, Mary Beth is mass 3. UJ is sitting closer to Mary Beth, yes? Okay, so that would be a more powerful variable, the radius, right, between them, because the distance is the more powerful variable that influences the gravitational force. But Mary Beth has less mass than Carl. He's a lot taller, right? So mass is also a variable that will influence the gravitational force. We can actually calculate that now. So where do you think UJ is more attracted to? We don't know that yet, right? Because you could have a mass that is bigger than the other one, but if the middle mass is closer than mass 3, then that could be more attracted to that. So right now we don't know. So here's an example. You have three 10-kilogram identical masses positioned in a straight line 2 meters away from each other. So this one is actually equidistant from each other, right? So I'm going to start sketching mass 1, mass 2, and mass 3. They're identical. Mass 1, 2. Okay, so the distance between them is 2 meters away. So 2 meters this way, 2 meters that way. Our question is, determine the net, that would be the net gravitational force on the central mass. So what I would like to do is, when I see a picture like this, or I sketch a picture like this, I'm going to put an asterisk on my focal point. So this is our focus. I'm looking at this mass 2. So the question, determine the net gravitational force on the central mass, is basically saying, what would mass 2 do? That's another way of saying that. What would M2 do? So basically, where would M2 go? Now, this is a very basic example. Let's look at the concept first. The masses are all identical, 10 kilogram masses each. The central mass is what we're looking at. Look at the distance between each one of them. They're 2 meters apart. So I'm looking for the net gravitational force on 2. Notice our designation is still Fg, but now I added the symbol sigma. Sigma means net, just like with the net force. Remember? Net means sum or total. So that's what we're looking for. Okay, without any calculation, can you just speculate what would mass 2 do with the presence of 1 and 3? Yes. Look at this. Mass 2 wants to go to mass 1. That's what mass 2 wants to do. But mass 2 also wants to go to mass 3 with the exact same amount of pull coming from mass 1 and mass 3. Okay? So you could imagine three identical people sitting side by side. Okay? The one in the middle is being pulled. This is kind of like a tug of war now. So mass 1 is pulling one person, mass 2, okay, that way, but the other one's also pulling it the other way. So what's going to happen to mass 2? If they pull hard enough, you're going to break their arms, and the person in the middle is going to stay right there, right where they are, right? So what would be the net force in this case? Now give me a number. 0. Exactly. You answered the question without answering any numbers, right? But we actually have to put some numbers in the other question. So I'm going to actually start with this one. So how do we do this? We're going to prove that this is actually going to be 0. So here's what we need to do. We need to look at the force on 2 exerted by 1. So Fg2 by 1. Now we're going to have to learn the language of physics here, right? So this is basically the force. I'm going to just write this once. The gravitational force on 2 exerted by 1. This is what that means. So the first number is what is being applied on. It's the force on 2. The second number means that's who's doing what. Does that make sense? Force on 2 exerted by 1. Okay, so we're gonna go F G 1 is equal to G M1 M2 over R squared. Because we're dealing with what is happening between mass 1 and mass 2. So let's take our calculator. Remember that G, I'm gonna just write G here so I don't have to keep writing it, is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. That's always gonna be given to you. Measured by Cavendish, you don't have to memorize that. Okay, so let's put our numbers here. 6.67 exponent negative 11 times mass 1, which is 10, times mass 2, which is 10, equals, and then divided by 2 squared. And the answer we have here is, now my calculator, it doesn't record everything, so I'm gonna have to, all I got is this one. Does any of you have calculators that do this? So you're gonna have to reset that so it actually gives you a better, so it gives you scientific notation, because it looks like a lot of it is cut off. I want you to pull out your calculator and actually check. When you're dealing with gravitational force, the forces are gonna be very small, because like we said, it's dominant but it's very weak, right? So it's gonna be a lot of negative forces here. So what did you guys get if you were to calculate this yourself? So I have to reset my calculator so it can actually give me scientific notation right away. And so this is what I got. So you actually have 1.67, let's keep 2 decimal place all the time, 1.67 times 10 to the negative 9 newtons. Okay, so that's the force on 2 by 1. And what I do is I'm gonna just put the arrow this way. That means M2 wants to go that way, or I will put left. Okay, so we're not using north, south, east, west right now because it's just going in a straight line. There's no directions necessarily, but left and right. Okay, so that's the force on 2 by 1. So what else do we need to do? We're gonna have to find the force on 2 by 3. And this one is gonna be G, look at this, M2, M3, because it is now between 2 and 3. Okay? And if you were to plug in the numbers, you know the numbers are exactly going to be the same, right? The masses are identical. The distance between them is identical. This is going to be 1.67 times 10 to the negative 9 Newton, except it's going to go this way. Or you could say right.
What's the value of R?
2 meters right here. So when you look at the net force on 2, what you're going to do is you're going to have this one, because it's going to the left and the other one is going to the right. Okay, you're going to end up subtracting the 2 numbers and you end up with 0, nothing. It's going to stay where it is, just like you predicted. Does that make sense? Okay, any questions about that? This is a vector question, as all forces are. So if they are going in opposite direction, you subtract them. Okay, example 12, let's take a look at, this is the exact same 3 masses that we have. Mass 1, mass 2, mass 3, each one is 10 kilograms. each one of them still 2 meters apart. Except now, you're looking at the mass located on the farthest left. So I put my asterisk on the farthest left. And I'm going to let you figure this out first by concept. Where do you think would mass 1 want to go? Okay? Take a look at the presence of mass 2. When you're dealing with gravitational forces, you have to deal with masses 2 at a time. So let's ignore mass 3. Let's talk about mass 1 and mass 2. Where would mass 1 want to go? Left or right? This way, towards mass 2, to the right. Now, forget about the presence of mass 2. Mass 3 is right there. Where would mass 1 want to go? Towards mass 3 or away from it? Towards mass 3. They're always attractive, right? So, look at mass 1. Mass 1 wants to go this way with respect to mass 2. Mass 1 wants to go that way with respect to mass 3. Which one do you think will be a stronger force? Between 1 and 2 or between 1 and 3? 1 and 2. Why?
They're the same size, so it's just like a
Closer. The answer is the distance is more powerful, right? So closer. Okay, so how do we figure out the net gravitational force on 1? That's the question now. Net force on 1. What do? We do it one at a time. This is going to be the force on 1 exerted by 2 plus the force on 1 exerted by 3. This, by the way, is always going to be added together, even though when I say added, this means this is the sum. This is a vector sum. So when I say add them, look at this in example 11. I added them as well, except when you add left and right, this is actually going to subtract, because you could think of this as negative, and that is a positive 1. So let's say this is negative 1.67. Now, I did not put negative. When you're dealing with gravitational forces, you don't have to say negative. You have to say the direction. So you have to think in your head. I'm gonna think in my mind that this is negative, okay? Because we're used to left as negative anyway. When the other one is exact opposite, that would be my positive. And if they're opposing each other, the negative and the positive will cancel. It's still added together. So when I say add the two forces, vectorially adding it, meaning it depends on the direction. If they're opposite, you actually say subtract, but we call it sum. Okay? All right, so you have to find this force first. So the force on 1 exerted by 2. We already know that from example 11, don't we? Because it's the identical question. Look at 1 and 2. We found that, didn't we? Right here. So the force is 1.67 times 10 to the negative 9 Newton. So G M1 M2 divided by 2 squared. And we've done that in the previous example.
What is G?
6.6. Can you guys write this down? I put it at the top so I don't have to keep writing it. Yeah, so that's going to be the G value, big G. Now we need to find the force on 1 exerted by 3. Notice that, look at this. Notice that because I'm looking for the net force on 1, I have to focus on FG1 and all the other masses that are interacting with it. I don't care about 2 and 3. I care about what 1 is going to be affected by. So it's between 1 and 2, or 1 and 3, or 1 and 4, or 1 in whatever, how many objects you have. Okay, so this time, look at this. I'm going to write this down in full. So this will become G M1 M3 over R squared. Okay, so 6.67 times 10 negative 11. Mass 1 is 10, mass 3 is also 10, but now the distance between them is different. What would be the R between 1 and 3? It's 4, okay? Because it's 2 plus 2. So, when we calculate this, let's take a look. 6.67 exponent negative 11 times 100, which is 10 times 10, divided by 16, equals, this is what we get. 4.17 times 10 to the negative 10 Newton. Were you predicting that this is going to be less? It is less. Why is it less? It's farther away. Look at this. It's a negative 10 exponent. Between 1 and 2 is a negative 9 exponent. That's the exponent they have to look at, not the numbers, right? So this is indeed less. Now we look for the FG on 1. So the net force on 1. All right. Let's take a look at the direction now. The direction. The force on 1 exerted by 2 is going to the right, that direction. Now, why did I say right? Because that's that way. So the arrow just goes towards where the mass is. Between 1 and 3 is going to the right as well. So it's going to go this way. Look at that. They're both going in the same direction. What do? Add or subtract them. So the sum is going to be a direct addition. So you're just going to add the 2. So I already have my 1 and 3 right here. So keep that. I'm going to go plus 1.67 exponent negative 9. So I just added the 2 numbers and we have 2.09 times 10 to the negative 9 Newton. Now what else do I have to put right here for the direction? I'm just going to put right. Okay, so just to make sure, I'll put right there. That's the final answer. So you need to make sure that you include all the masses that are affecting whatever mass you're focusing on. In this case, mass 1. Mass 1 is affected by 2 and 3 independently. 2 masses at a time. So the formula doesn't tell you GM1, M2, M3. There's no such thing. It's between 2 objects at a time. And then you just find the sum. Now we get into example 13. Now before we get to a more complicated example, do you guys want to do another one? Should I add another one or we're good? We're good? Okay. Don't worry. On the back of this, and I will give you another review handout before the test, you will get review questions of everything combined. So would these 2 examples be enough for now to move on? You got it? Okay. Now we're going to get into a different shape. So we're looking at 3 different configurations. Linear, which is a straight line. We're going to look at triangles of different kinds. You know, you have the isosceles, equilateral, and scalene. And then we're going to look at parallelogram, square or rectangle. Okay? Forces in different shapes. Okay, so example 13. You have an equilateral triangle. What does equilateral triangle mean? What do we know about that?
Equal sides, equal angles.
Right? Equal sides, equal angles. So it would be something like that. And this would be the same. What would be the angles of each one? By rule of 180. Every triangle when stretched out is a straight line, 180 degrees. Rule of 180 tells you, right? All 3 sides must equal 180. But if you have 3 identical ones, it's 180 divided by 3. So each one will be 60 degrees each. Okay, those are the things we know about equilateral triangles. Okay, so let's draw an equilateral triangle. And then you have mass on each of the corners. Okay, so 3 identical 10 kilogram mass. Again, it's exactly the same mass as we talked about in 11 and 12. So 10 kilograms each. And 2 meters away from each other. 2, 2, and 2. Okay, which one are we looking at? The gravitational force on the mass on the top of the triangle. Just so we can focus our mind, some strategies that make it easier. I put an asterisk so I know my eyes are focused on that asterisk. So the top mass. All right. So we need to find the force. Let's call them 1, 2, and 3 because it didn't say which is which, right? What do you guys want to call the top one? 1. Okay, let's call that one 1. I want to go clockwise. Might as well. Let's call this one 2 and this one mass 3. Okay, so let's go and find force on 1 exerted by 2. Now, in terms of magnitude, we know that force on 1, see that? 1 and 2. What can you say about the numbers? Just the numbers. 1 and 2 versus 1 and 3. Why would they be equal? Yeah, same distance, same masses. We're not looking at angles just yet. We know that force on 1 and 2 is equal to force on 1 and 3 in terms of magnitudes only. Okay, that means the amount, the number only will be the same. So knowing that, that will save you time. Instead of calculating both, just calculate 1. So we're going to go force on 1 by 2 is G M1 M2 over R squared, which is going to be exactly the same as force on 1 by 3. Okay, now we already know this, don't we, from the previous question. Makes it handy. Value. So G M is 10 times 10 divided by 2 squared. What do we have? 1.67 times 10 to the negative 9. So we already know that. So far so good. Now what? Let's take a look at what mass 1 is going to do, because that's basically what the question is. The net gravitational force would be asking, what is mass 1 really attracted to and where is it going to go? Look at this. This mass 1, if I use a different colored here, it makes it easier. Mass 1 wants to go this way. I'm going to put an arrow. That's where mass 1 wants to go with 3. Mass 1 is going, oh, I like number 3. It's kind of like, I'm going to imagine the equilateral triangle as me. I'm that one, mass 1, okay? Mass 2 is Jessica over there, and Brenda is mass 3. So imagine, can you guys take a look at the 3 of us? Look, we're about an equilateral triangle, right? See that? Okay? So I'm looking at Jessica and I go, she's a nice person, I like her, I want to go and talk to her. But then I look at Brenda and go, she's a nice person, I want to talk to Brenda. So I am now torn between these two wonderful human beings and I want to go see and spend time with them. Where do you think? Now, they're also pulling me. Think of that as, I want to go to them, but they're pulling me. So my arm is going this way and Brenda's pulling me that way. Where am I going to end up going? Where? Look at this diagram. Where would it be? Give me a direction. Up, down, north, side, left, right. Where? Is it exactly down? Yes. I'm going to end up where Carl would be. I'm going to end up where Ibrahim is. Okay? Isn't that funny? I want to go to Jessica. I want to go to Brenda. I ended up to Ibrahim. Not exactly to the end though. Not all the way here. I'm going to go end up right here. It's actually going to be just close to Carl. Okay? So this is our prediction. There you go. Equal. Those two green arrows. But I'm going to actually end up right there. Is that what we're predicting? Yeah? So let's figure out if that is indeed true. How do we do that? What do you guys think? We go back to vectors. So here's vector 1 going this way. Okay, so I'm going to call it vector 1. This is actually force on 1 by 3. The other one is going this way. Force on 1 by 2. And they are exactly the same length. And look what happens when you combine the two. Whoa, look at this. Head to tail. We just add them together like that. And where is it going to go? Look at my picture. Force on 1 by 3 is this magnitude. This one right here. Force on 1 by 2 is that magnitude going this way. Where is the line that connects the beginning and the end? Straight line going down. That is the net gravitational force on 1. But how do we actually find that? Can we just add these two? Can we? Can we add these two numbers? No, we can't, because this is crooked. It's not a straight line. So how do we do that? Well, by vectors, right? We could go Vx and Vy. Remember the chart that we learned in Unit 2? So I'm going to call this vector 1 and vector, I'll call this actually V1 and V2. So I'm going to call V1, V2, and this is the VR. So we're back to that method. But the question now becomes, what is this angle right there? What is this angle right here, guys? Because I went this way, and there's a line that goes straight down. So what angle is that little bit? This angle right here, what's that? How did we know that? Because remember, in an equilateral triangle, the whole thing on the inside is equal to 60. So if I'm just going to cut half of that, I'm going to take half. This is going to be a 30-degree angle, right? Does that make sense? Okay, so we figured out that angle. What about this angle right here? That little bit. They have to equal 90. Remember, this is a 90. Every corner is 90. So if down below is 30, up here would have to be 60. Make sense? You're basically saying that in this triangle right here, because that's 30, this has to be 60. See that? Okay? All right. But what about V2? Let's talk about the angles before we plug in the numbers here. So again, this triangle here, okay, look at this. See if I can do a letter Z right here. What is this angle inside? It's also 60. Okay. You guys are familiar with trigonometry. You've done triangles before, right? You know the rule. It's called the transversal rule. That if you have a letter Z, kind of like it's called the Z rule, transversal rule. See this 60 right here? That's also going to be the same there, 60. Which means then, what angle is this? Well, you see this thing right there? What's the angle down below? That would be the other side of the triangle. This one right here. That's also 30, isn't it? See this line here? Remember this line I took from there? That's 30 also. This is 30 degrees, which means this is 60. Okay. Do you guys remember when we were doing vectors, the method that I used? When you talk about the x-axis, we can use that as cosine. And this is sine. But the angle has to be from the x. Okay, do we know the axis angle? Yeah, we do. So this is 60, isn't it? Right there, angle from the x is 60 degrees. So what I'm going to do is, what is the x going? Is it a negative or positive? The first one, the first line. Going to the left. This is 0 right here. He went to the left, so I'm going to put negative 1.67 to the negative 9, but I'm going to put cosine of 60 because the angle has to come from the x-axis. This is x, horizon, the horizontal. Okay, and then we're going to have that number. Okay, so then we have 1.67. Can you guys make sure you're doing this as well? Negative 9 right there. I'm on degree, yeah, times cos of 60. Okay, so we have 8.35 times 10 to the negative 10. Does that make sense? We're finding the x-axis. So this is what I found so far. That one right there, the x-axis. Now how do you find the y-axis of this? What do you mean do the opposite? Is this a negative y or positive y? Went down, right? So again, it's negative 1.67 times 10 to the negative 9. But we put sine of 60. We have to use the same frame of reference angle. Okay, so this is not a 45-degree angle. We have to calculate that again. So 1.67 exponent negative 9 times sine of 60. So this is negative 1.45 times 10 to the negative 9. Remember, you're dealing with very small numbers here. Negative 9. So don't drop it, the numbers, and round it off to 1.5. Okay? Leave it to do 2 decimal place at least. I'm going to leave you to do the second vector right here, vector 2. Do the same thing that we did. The only difference now is that we're dealing with a small number, but we're still using cosine and sine of whatever angle from the x. So I want you to try to do this one, please. V2. Do it on your own. I will write it down here so you can check. I'd like you to try. Okay, so the answer is up there. So as you predicted, the x are going to cancel each other out, okay? Because this thing here is going to the left, this one is going to the right, okay? So they do cancel each other out. You have nothing on the x-axis. So look at this. This is going that way, but this one's going this way, okay? They are going to cancel. So look at this one here. So for the second vector, the x is positive because it's going to the right. This is now the 0, right? Going to the right, so it's positive 1.67, exponent negative 9, cos of 60, and you get a positive number that is the same as that, so you get a sum of 0. Okay, when you combine those two green numbers that I have, you get 0. On the y-axis, it's still negative because it's still going down, so you end up with twice as much, but in the negative direction. So your final answer, the net force on 1, you'll end up with a negative 2.89 times 10 to the negative 9, right? Or preferably, this would be the preferred answer. We don't put the negative number, so you'll just say 2.89 times 10 to the negative 9 Newton, and then the direction. So in this case, that's just going down. So that's the final answer that I would put that in the box. Is that good? Any questions about this one? Okay, we're gonna need to do more practice with the triangles. Triangles are the hardest ones. Okay. Let's try another a couple more, okay, and then you have a square on that side. Okay, let's do example 14. So another equilateral triangle. This is actually the same as the one before, except you're now looking at the bottom left of the triangle. So I'm gonna draw my equilateral triangle again. So I'm gonna call this one still mass 1, mass 2, and mass 3, the same as before. 1, 2, and 3. They're still 2 meters apart and still 10 kilograms each. This time we're going to look at the bottom left. So this is gonna be the net gravitational force on 3. That's our question. All right, again, what do we know here? We know that the force on 3 exerted by 1, this is what it wants to do, right? Here's number 3. It's looking at 1 going, hey, I like that one. I'm gonna go there. And number 3 looking at 2, going, hey, I like that one too. And it's the same distance apart, and it's the same masses. What can you say about the numbers?
The force of 1 on 3 and the force of 2 on 3 are equal.
They're equal again, because it's depending on mass and the distance, right? Now, because it's an angle, it's just a matter of where is it exactly gonna do? Where is it gonna go? So force on 3 by 1 is equal to the force on 3 by 2 by magnitudes, which is equal to, we did that in example 13, right? So we have the number. I'm just gonna write down 1.67 times 10 to the negative 9 Newton. That one we know. This time though, the vector directions are going to be different. So where do you predict it's gonna happen? Where do you think it's gonna go? Mass 3. It's the same equilateral triangle, it's just askewed from your point of view. You know what? Look at this. If I were to take my page and kind of go like that, see this? That's the top triangle that we just did, isn't it? But that's not what we're dealing with here, because we have to deal with the position of the triangle as described. So we just do it by vectors. So let's make our chart. Vx, Vy. So I'm gonna call this my vector 1 this time. It just makes it easier instead of keep rewriting the designations there. So there's my V1. Make sure though that you're labeling your work, because it doesn't matter which is which, as long as you know in your head and on paper, so I know what I'm looking at, which is which. Okay. Okay, so we have to identify these angles. What is the angle between 1 and 2 right here? This angle right there. 60. It's actually going, the V1 that we call V1 is going this way, and it's 60 degrees from the X, right? There's our V1. You see it? You guys see the V1? 60 degrees, right? Draw that on your picture and see if that makes sense. What about V2? How are you gonna draw V2? That's the easiest one, because look at V2. Going to the right. That's it. V2 is going to the right. Is there an angle to that? No, there isn't. It's just going to the right. Okay, so we put our numbers down. We already know the magnitude right here. Is X positive on V1 or is it negative? There's the origin. Going to the right. Positive 1.67 times 10 to the negative 9. There's an angle to this one, so we put cosine of 60, which we know from before, don't we? 8.35 times 10 to the negative 10. Positive. What about the y-axis? This is going to have to be a positive 1.67 times 10 to the negative 9 sine of 60. Do we have that number somewhere? Look at example 13. Okay, look at that. Same number, except this is positive, right? So positive 1.45 times 10 to the negative 9. Is that okay? Now, I want you to trust yourself with V2. What is V2's number gonna be? Remember, the number is 1.67 times 10 to the negative 9.
And
There's
there's no angles.
no angle.
They were just
Is it positive or negative?
positive.
That's it. 1.67 times 10 to the negative 9. How do we get these numbers, guys? This is the GM1 M2 over R squared, which we calculated previously. What about the y-axis of V2? Look at this arrow. Does that even have a y-axis? 0. Okay? Check our sign. X is positive. Y is positive. This one's all X positive. Now what do? We combine. These are both positive, so we just straight up add them up. 8.35 exponent negative 10 plus 1.67 exponent negative 9. And you get... Can you guys tell me what you have? I want you to try these. Okay, who's got a number? It helps when you get the answers right off your calculator. What did we get? I'm gonna have to double check my answer now. 8.35 exponent negative 10 plus 1.67 exponent negative 9. That's the same thing I got. 2.51 times 10 to the negative 9. Double check. They're both positive. Look, which means when I redraw my picture, this is going to be positive going that way, and this is going up this way. So X is larger than Y. I'm going to draw it like this, and we got to find the angle. So this is the first on 3. So that's where it's going to go. As we predicted, it's going to go somewhere here, and that is the direction right there. Okay, so because you have an X and Y and it's 90 degrees, we'll go Pythagorean. So X and Y, right? So the net force on, so the resultant is going to be your X, whatever that is, squared, plus this value squared, and take the square root. Okay, Pythagorean theorem. Because we have combined the X's and the Y, we got a 90-degree triangle. It's a good method. It makes a very complicated triangle into a 90-degree triangle. So you have Pythagorean. So 2.51 exponent negative 9 squared that plus 1.45 exponent negative 9 squared equals, and then square root 2.89 times 10 to the negative 9 newtons. Okay, it's the same as number 13. Like I said, it's just turning the picture upside down, but what matters now is the angle. So this angle here by tangent theta, okay, opposite over adjacent, right? So opposite is the y, so 1.45. Look what you're always strapped with time, right? Look at the exponents are the same. So to find the angle, all I did was opposite 1.45 divided by 2.51 if the exponents are the exact same thing. Okay, which means if you divide this by that, you get 1 anyway. So I just took the first numbers and I got this, and second function tan, and it's 30 degrees. So we'll have to use north, south, east, west now. 30 degrees from, what direction is this? East, going up north. That's your final answer. So the same answer as number 13 with magnitude, except this one is an angle. That makes sense? You'll need more practice with this one. So I will suggest when you get home, take a blank piece of paper, cover your solution, do that, and then check your answer. Okay? So that's the best way to do this, is to try to do it again on your own, step by step. Okay, can we get to the last example? Okay, I'll give you some time if you're still copying. Finish it up, let me know, okay? Because might as well finish copying the notes.